Hello students, I hope you all are safe and living happily. In the previous section we have discussed Gauss theorem and its applications, right? In the unit electrostatics we have discussed potential difference, electric field, electric flux. Today we are going to start with a new topic which is capacitance. And the instrument which is used to store electric charge, that is capacitor and its principle. So these are the few topics which we will be discussing in this particular session, right? So let's begin with capacitance. Consonant of this particular term, capacitance, something related to capacity, something related to ability basically, right? So capacitance actually it's a physical quantity which signifies the charge storage ability of a conductor or of an arrangement. So capacitance literally is the charge storing ability of a conductor or an arrangement, right? It denotes the capacity or the ability of a body to store electric charge. This was the theoretical statement, right? Now, how to measure the capacitance of a body, right? So let's deal with it mathematically. We all are aware that when charge is given to a body, then obviously the potential of the body tends to increase, right? Whenever charge is given to a body, the potential tends to increase. So suppose on giving charge Q to a body, suppose its potential is V, capital letter V. So mathematically, we can write Q is proportional to V. As you keep on giving charge to the body, the potential of that body will keep on increasing, right? So mathematically we write it like this: Q is proportional to V. Now in order to eliminate this proportionality sign, we need to introduce some constant. So in this case, the constant is C. Block letter, capital letter C. This C, which is the constant of proportionality, is known as capacitance of the body under consideration. So this C is known as capacitance. Right? It depends on various factors. We'll discuss its SI, its Cgs unit as well. We'll try to define it mathematically as well. So capacitance actually mathematically it may be defined as Q by V. So it may be defined as the ratio of the charge contained in the body to the potential of the body. So that is how capacitance may be defined. Now its SI unit of capacitance is farad. It is denoted by capital letter F. So let's define farad. When the capacitance of a body is said to be 1 farad. Now look, 1 farad would be equal to SI unit of charge is coulomb, SI unit of potential is volt. It's very simple. The capacitance of a conductor is said to be 1 farad when 1 coulomb of charge is required to raise its potential through 1 volt. Right? So this is how 1 farad is defined. Now let's discuss its Cgs electrostatic unit. The Cgs electrostatic unit is stat farad. Cgs electrostatic unit of charge is stat coulomb. And you are aware Cgs electrostatic unit of potential is stat volt. So making use of this fact, 1 farad is equal to 1 coulomb divided by 1 volt. So what to do is 1 coulomb, you might remember, it is 3 into 10 to the 9 stat coulomb. 1 volt, it is 1 by 300 stat volt. So 1 farad would be equal to 9 into 10 to the 11 stat coulomb divided by stat volt. That will give us stat farad. So this gives the relationship between the SI and Cgs Electrostatic Unit of Capacitance. Farad is the SI unit of capacitance and stat farad is the electrostatic Cgs unit of capacitance, right? So this is the relationship in these two. Now capacitance of a conductor, that is the charge storing ability of a conductor, the quantity up to which a body can store electric charge, that is dependent on various factors. In the subsequent sections we will prove it mathematically, but in the present session let's discuss it theoretically. The value of C, it depends upon the nature of the medium in which the conductor is placed. Whether it is placed in air or vacuum, whether it is placed in some medium. So it does depend upon the nature of the medium in which the conductor is placed. So that's the first point, right? Second point is, it depends upon the dimensions of the conductor. What I need to say is that there are various types of capacitors which we will discuss. There are parallel plate capacitors, cylindrical capacitors, spherical capacitors. So in all these scenarios, the capacitance of each of these capacitors depends upon their dimensions. Dimensions means shape and size. So it does depend upon their shape and size as well. So these are a few factors on which the capacitance of a conductor or an arrangement depends. Clear? Before proceeding, I must tell you a very important fact. Earth can be considered to be a spherical capacitor, solid spherical capacitor, right? So before we move forward to the next topic, let's try to find out the formula for the capacitance of a spherical conductor, and then we will find out the numerical value of the capacitance of Earth, right? Let's proceed with that. So, we are going to find out the expression for the capacitance of a spherical conductor. Capacitance of a spherical conductor. Suppose we consider a sphere of radius r. Let us consider a sphere. This is a sphere of radius r. This is the center and its radius is r. And charge is uniformly distributed over it, throughout its volume, right? Charge Q is distributed uniformly over it. Now as we are aware, this is the formula which we are going to use, Q by V. Net charge on the sphere is suppose Q, which is uniformly distributed. Now this is the formula which we are aware of. Just now we have done it. The value of potential at any point on the surface may be written as 1 over 4 pi epsilon Q by R. This is the second one. So we are considering this conductor to be placed in air or vacuum, right? So this is the potential at any point on the surface of the conductor. In that scenario, the entire charge may be assumed to be concentrated at its center, right? So in that case, potential is given by this formula. Now substitute this value of V over here. What you get is Q divided by 1 over 4 pi epsilon Q by R. So we will be left with 4 pi epsilon R. This is the formula for the capacitance of a spherical conductor of radius R. Remember this, right? So as you can notice, with the increase in the radius of the sphere, its capacitance will also keep on increasing. So it is linearly dependent. So if this represents the radius, this represents the capacitance, so it will be like this. Isn't it? Straight line, indicating the linear dependence between these two. Now, regarding the capacitance of Earth, you are aware, for all practical considerations, we consider Earth to be perfectly spherical. Actually, it is egg-shaped, ellipsoidal, isn't it? But for all practical considerations, we can consider it to be a sphere of radius 6400 km. So radius of the Earth is 6400 km. Or in SI, it can be written as 6400 into 10 to the 3 meters, or 6.4 into 10 to the 6 meters. That's the value of radius of the Earth in SI. Now what we do is, you can substitute the value of R, Earth over here, and substitute the value of 1 over 4 pi epsilon, isn't it? Also, 1 over 4 pi epsilon. You're all aware of it. Its value is 9 into 10 to the 9 Newton meter square per coulomb square. So the capacitance of the earth would be equal to 4 pi epsilon. It will be 1 over 9 into 10 to the 9 and radius of the earth, that is 6.4 into 10 to the 6. So we will get the answer. The answer would be, you can easily solve it. It will be 711 into 10 to the minus 6 farad or 711 microfarad. This is the capacitance of the earth. So earth, when treated as a spherical conductor, its capacity is 711 microfarad. Point to be noted over here is earth, in spite of its huge size, its capacitance is only 711 microfarad. So the thing which we conclude is that farad is a huge unit of measuring capacitance. Farad is a very, very large unit. So very often we make use of these units. Millifarad, it is 10 to the minus 3 farad. Microfarad, it is 10 to the minus 6 farad. And 1 microfarad or 1 picofarad, it is 10 to the minus 12 farad. So these are some of the units which we oftenly use, right, in discussing the capacitance of a conductor. Now, we have seen over here, although earth is so huge, still its charge storing ability is very, very small. So we require some arrangement. It may be combination of more conductors which can store huge charge in small space. So such a device is known as a capacitor, right? A single conductor can't store huge charge. So we will try to understand a suitable combination of conductors with a small gap between them and maybe a dielectric placed between the space between the two conductors. Then that arrangement will be capable of storing a huge amount of charge in very small space. That arrangement, that suitable arrangement of conductors which is capable of storing huge amount of charge even in small space is known as capacitor, right? So let's start with that topic and we'll also discuss its principle, the principle of a capacitor. So as I stated, farad is a very big unit of measuring capacitance, and every conductor has got some charge storing ability, but that charge storing ability is too small, very, very small to be used for any practical purposes. We have seen earth, although of such a huge size, still is able to store only 711 microfarad. Its capacitance is 711 microfarad, which is very small. So in order to increase the capacity or in order to increase this charge storing ability, conductors are arranged suitably parallel to each other with a small space between them, and that space between the two conductors may be filled with dielectric or some other insulating medium. In such a scenario, it is found that the charge storing ability of that arrangement increases enormously. So that suitable arrangement of conductors is known as a capacitor. So students, capacitor means these are the electronic devices which we very often use in every electronic circuit almost. So capacitor is an arrangement comprising of suitable arrangement of two conductors with a small gap between them, which may be filled with some dielectric or non-insulating medium, and the charge storing capability or ability of that arrangement is very, very large. So that suitable arrangement of conductor is known as a capacitor. Now let's try to understand its principle. Let's try to understand the principle of a capacitor, or the principle on which the working of a capacitor depends, right? Let us consider a conductor over here. Let us consider a conductor A over here. As I told you, every conductor has some charge storing ability. Whether it is a small pin or a small nail, if you give charge to it, it will store definitely some amount of charge, right? So this is a conductor. Obviously, it will have some charge storing ability. When charge is given to it, it will keep on storing charge. Up to a level, up to a saturation point. So as the charge is given to it, its potential will keep on increasing. Further charge is given to it, its potential will still increase. A stage will come when it will attain maximum potential. Saturation value of potential. Thereafter, if additional charge is given to it, it will not accept any additional charge. Instead, it will lose that additional charge to the surroundings. So, it has a limitation on it, that it can't hold charge beyond a certain value. So, this can store charge, but its charge storing ability is very, very small. I hope you have understood the first case, right? Let's consider B. Same conductor A. This is the charged conductor. Now what to do is, let's place an uncharged conductor over here. B is the uncharged conductor. This is the uncharged conductor. Now what happens is, this is a conductor which is uncharged. Net charge is 0, but being conductor, it will have large number of free electrons, right? So as soon as this uncharged conductor is placed near this charged conductor, redistribution of electrons will take place. Earlier electrons were distributed uniformly. Now what happens is, this phase will acquire a net negative charge. All the electrons will tend to get attracted towards this, right? So this region, the farther region of plate B, will have deficiency of electrons, and accordingly it will acquire a net positive charge. So redistribution of electrons will take place. Students, it must be remembered, merely redistribution of charge is taking place. Net charge over here is still 0. Still B is uncharged. Net charge is 0. Simply redistribution is taking place, right? This is suppose a mean distance. Now this is negative charge. The distance is R1. This is positive charge. The distance from this plate A is R2. Obviously R2 is greater than R1. It's pretty clear from the diagram. Now the negative charge so developed on the inner face will tend to decrease the potential of A. Due to negative charge, the potential decreases. While on the other hand, the positive charge so developed on the farther face will tend to increase the potential of plate A. But can you tell me whose role will be dominant? Whose effect will be more dominating? It will be of negative charge, because the negative charge which is induced, or rather which is developed on the inner face, is at a much closer distance as compared to the positive charge that is developed on the farther face of plate B. So again I am repeating, the negative charge developed on the inner face will tend to decrease the potential of plate A, while the positive charge so developed on the farther face of plate B will tend to increase the potential of plate A. But the negative charge being closer to plate A, the overall effect will be that the potential of plate A slightly decreases. It slightly decreases. So, now it is in a position to accept more charge so as to raise its potential back to its saturation level. So what I mean to say is that as its potential slightly decreases, some additional charge can be given to it, and some additional charge it will accept. So as a result, due to the slight decrease in the potential, there is slight increase in its capacitance. So point B, what does it tell us? On placing an uncharged conductor near a charged conductor, the potential of the charged conductor slightly decreases, and hence its capacitance slightly increases. So when you compare these two, this is the preferred arrangement. Here the capacitance is very, very low. Here the capacitance slightly increases. Right? Now consider the third case. This is again plate A, which is considered to be the charged one. This is plate A. This is charged one. This is plate B, which is uncharged. But due to the redistribution of charges, it will acquire a net negative charge, and the farther face will acquire a net positive charge. Now what to do is, conductor B is earthed. Now what happens is, electrons from the earth will come and it will nullify those positive charge. It will get nullified. So this B will be left with only and only negative charge. Now what happens is, due to the neutralization of that positive charge, only negative charge is left, which tends to decrease the potential. So now the potential of plate A is found to be decreased considerably. So as a result, it is capable, or it is in a position to accept that much more charge, so as to again raise its potential to the saturation point. So due to the decrease in its potential drastically, its capacitance increases enormously. So this forms the principle of a capacitor. So students, principle of a capacitor. Working of a capacitor is based on the principle that when an earth connected uncharged conductor is placed near a charged conductor, then the potential of the charged conductor decreases drastically, and accordingly the capacitance of the arrangement increases tremendously. So that forms the principle of the capacitor, right? Let's reconnect these concepts. First, we have considered a conductor. When charge is given to it, it will accept it. It will accept till its potential becomes maximum. Once it attains its maximum potential, it will not further accept any charge. The additional charge given to it will lose to the surroundings. So this has got some charge storing ability, but it is too small to be used for any practical purposes. Let's come across B case. Here an uncharged conductor is placed near a charged conductor, right? This is an uncharged one, but since it is a conductor, it will contain a lot of electrons. So those electrons get redistributed. So this inner phase will develop negative charge, the farther phase will develop positive charge. So this inner phase where negative charge is developed, it will tend to decrease the potential, while the positive charge will tend to increase the potential. But the negative charge being closer to this plate A, the overall effect is that on placing this uncharged conductor, its potential will slightly decrease, and hence its capacitance will slightly increase. Slightly increase. Its capacitance will slightly increase. Here, on connecting the plate B to the earth, what happens is the positive charge get neutralized from the electrons coming from the earth. So it will be left with only negative charge. These are the bonded charges, right? So this negative charge will tend to decrease the potential of plate A tremendously. So as a result, due to the decrease in the potential of plate A drastically, the capacitance of this arrangement increases tremendously. So this forms the principle of the capacitor. Students, I hope you have understood it. So we will discuss it in the next session.